Hello, everyone. Last class, you learned about how to change grams to moles and then also how to balance chemical reactions. So, in this chapter, chapter 4, we are going to learn about the stoichiometry of chemical reactions. And to perform stoichiometry, you need to know how to convert grams to moles, and you also need to know how to balance chemical reactions. So, I strongly recommend if you still have trouble converting grams to moles, I recommend going back to the lecture and reviewing it, and also going back to balancing equations and reviewing them. Okay, now what is stoichiometry? Stoichiometry is basically the relationship between reactants and products. So in industry, in order to prevent wastage of chemicals, you need to know how much reactants you need to begin with in a chemical reaction if you're looking for a certain yield of the product. You also should be able to predict how much product you're going to produce if you use certain amount of chemical reactants. So that a study of those chemical relationships between reactants and products is called stoichiometry. Okay, first let's review balancing reactions. Remember, in chemical reactions, you're making bonds, new bonds, you're breaking some bonds. Atoms are changing their positions, but no new atoms are formed and atoms are not destroyed. So you have to preserve the law of conservation of mass. And for this reason, we have to balance chemical reactions. That means you have to make sure that atoms in a chemical reaction are the same on the left hand side and on the right hand side. You have the same number of atoms of each kind on the left and the right. When you balance reactions, remember you have to change only the coefficients, meaning the numbers that come in front of the chemical formula. You don't change the subscripts, okay? And another thing you need to remember is the coefficients must be in the simplest whole number ratio after you balance a reaction. So here we have a reaction of magnesium wire burning, okay? Burning means it is reacting with oxygen in the air. Remember, oxygen supports combustion, okay? So our reactants are magnesium and oxygen. And eventually, after you burn it, you're going to be left with a white colored ash that is magnesium oxide. It's a white colored solid. So that's your product. So let's write the formula for reactants and products. Magnesium is just Mg. Oxygen gas is O2. Remember, it's not just O, it's O2. And magnesium oxide is MgO because magnesium is in the second group, so it has 2 plus charge. Oxygen is in the sixth group. It's 2 blocks away from the noble gases. That means it likes to accept 2 electrons and become O2 negative. So the formula for magnesium oxide is just MgO. So once you write the reactants and products, next step is balancing the chemical equation. So balancing means you should have same number of atoms of each kind on both sides. So you have one magnesium here. You also have one magnesium here. Magnesium is balanced. But oxygen is not. You have 2 oxygen atoms on the left, but only 1 oxygen atom on the right. So to balance oxygen, you change the coefficient of MgO to 2, okay? And that has changed the number of magnesiums also now. Remember, 2 MgO means you have 2 of these, MgO and another MgO, okay? That means you have 2 magnesiums and 2 oxygens on the right, okay? So now magnesium is not balanced because there are 2 here and there is 1 here. So if you change the coefficient of magnesium on the left to 2, now you have 2 magnesiums on the left as well as the right. Okay, the reaction is balanced now. And what this means is for every 2 magnesium atoms, so for this reaction, 2 magnesium atoms will react with 1 oxygen atom and they will form 2 MgO units. Okay, so this is telling you the coefficients are telling you the ratio in which magnesium and oxygen react and the ratio in which the product is formed. Okay, so you can say 2 magnesium atoms, so you can write two Mg atoms react with one oxygen molecule, okay, reacts to produce, and then two MgO molecules are produced, okay. You can say formula units here because this is a ionic compound. Formula units is more appropriate, but let me, for simplicity, just write molecules, okay? So two magnesium atoms, you can think of this as a conversion factor. Two magnesium atoms reacting means one oxygen molecule reacting, okay? And or, in other words, two magnesium atoms reacting means two magnesium oxides are formed. So in this reaction, if one oxygen molecules react, that's equivalent to forming two magnesium oxide. So think of these as conversion factors. They're telling you the number in which they react. If you scale it up, you can say if you have 2 dozen magnesium atoms, then they will react with 1 dozen oxygen molecules and they will produce 2 dozen magnesium oxide. Okay, you can scale this up and say if you have 2 moles, if you have 2 moles magnesium, then it would take 1 mole oxygen, okay, then it would need 1 mole oxygen to react and it will produce 2 moles of magnesium oxide. Okay, so the balanced reaction is telling us the molar ratio. So remember that this is the molar ratio. Okay, the molar ratio in which chemicals react in this reaction is 2 to 1 to 2. All right, let's practice balancing one more reaction. This time, I'll show you what I mean by simplest whole number ratio. Okay, you can never have fractions in your chemical reaction after you balance it. So here's an example. Acetylene. Acetylene is the gas used in welding torches. Um, it's highly exothermic, meaning it produces a lot of energy, and that's why you use it in welding torches. Okay. So you have acetylene reacting with oxygen, giving carbon dioxide and water. We need to balance this. So what do we start with? Remember, oxygen is on the left in one substance, but it's in two substances on the right. So to balance oxygen, I don't know whose coefficient I need to change. So let's not begin with oxygen, okay? Carbon is only in one substance on the left, it's in one substance on the right. So I know that I have to change only one of these coefficients, okay? So let's begin with carbon. So since you have 2 carbons on the left, you would need 2 carbons on the right. So you would put a coefficient 2. Now, how about hydrogens? You have 2 hydrogens on the left, 2 hydrogens on the right. So hydrogens are already balanced. So let's count the oxygens now. You have 2 oxygens on the left, and you have 4 oxygens here, 4, plus you have 1 oxygen there. So 4 plus 1, that's 5. You have a total of 5 oxygens on the right. So how do we get 5 oxygens on the left? What should I multiply 2 by so that I get an answer 5? It's 5 over 2. If I multiply the number 2 by 5 over 2, then the 2 cancels out and you will be left with just 5. So the coefficient here should be 5 over 2, and it makes sense mathematically, okay? Because 5 over 2 times 2 will give you 5. But since you cannot have fractional coefficients in your balanced equation, you have to multiply everything by 2. You have to double all the coefficients, okay? So if you double all the coefficients, here the coefficient is just 1. So when you double it, you get 2C2H2 plus 5 over 2 times 2 is 5. So I'm doubling it. I'm doubling everything. Now we have 4CO2 plus 2H2O. So that's your balanced chemical reaction. Okay? And what does it tell me? It tells me the molar ratio. So it tells me that 2 moles of C2H2 will react with 5 moles of O2, and they will produce 4 moles of CO2 and 2 moles of H2O. Okay, this is the information given by the balanced chemical reaction. It gives me the molar ratio in which the chemical species react and are produced. Now we can use this information to do stoichiometry. So what is stoichiometry? Stoichiometry is the relationship between relative quantities of any two substances in this reaction. Okay, so here we have a balanced chemical reaction. So it's basically hydrogen gas. Just notice that we are putting the states right after the substance in parentheses. So the G here stands for gas. Anyways, so this is telling me that hydrogen and oxygen react in 2 to 1 molar ratio, and they produce water according to this 2 to 1 to 2 ratio. So I can write that down. So 2 moles of hydrogen used is also equivalent to 1 mole of oxygen being used, and that's equivalent to 2 moles of water being produced. So if we want to predict, suppose I burn 6.4 moles of hydrogen instead of 2 moles. Suppose I burn 6.4 moles. How do I predict how much oxygen is needed, or how much oxygen is used for any other amounts? This you can do this using the 2 to 1 stoichiometric ratio. Okay, so if we have a problem like this, how many moles of oxygen are needed to completely burn 6.4 moles of hydrogen? First, let's think rationally. For 2, 1 is needed. So for 6.4, half of that will be needed, because as you can see, 1 is half of 2. Okay, so oxygen used is half of hydrogen used. So if we have 6.4 moles of hydrogen, then you should use only half of that, which is 3.2 moles of hydrogen. Okay, you can set up the same, what I just said, using a dimension analysis. So since this is our starting unit, and the unit we are looking for is moles of oxygen used, okay? And the molar ratio is 2 to 1, so you put moles of hydrogen on the bottom because you want to cancel that out, and you put moles of oxygen on the top because you want to produce that. Basically, that's the unit what you want to get out of this. So now you put the molar ratio 2 to 1. 2 moles of hydrogen is 1 mole of oxygen being used. Calculate that and you get 3.1. Okay, so from now on, we are just going to show the dimension analysis steps to show clearly how we are getting from one substance to another substance. Okay, likewise, you can relate hydrogen to water, and the ratio is 2 to 2, or in other words, just 1 to 1. Okay, so if you're burning 2 moles of hydrogen, you also get 2 moles of water. So if you're burning, let's say, I'm using the word burning because burning basically means anything reacting with oxygen. Okay, so if you're burning 6.4 moles of hydrogen, then you should also expect 6.4 moles of water, because they're in the same equivalent ratio. Okay, so the way to set this up in dimension analysis is, this is what you have, and you're looking for moles of water being produced, and the ratio between those two is 2 to 2. So you put that ratio 2 to 2 and cancel out the units, moles of hydrogen, and then you go to moles of water. So you get the same value now, 6.4, because of the 1 to 1 ratio, or 2 to 2 ratio. All right, so here's the takeaway from what we did so far. Suppose you are given moles of, if you know moles of one substance in your balanced equation, let me call that substance as substance A, then you can convert that to moles of another substance, let's call that substance as B, using the stoichiometric coefficients, okay? Or in other words, molar ratio. You can say molar ratio, or you can say stoichiometric coefficients. So using the molar ratio, you can go from moles of one substance to moles of another substance. Okay, so keep in mind anytime you have a reaction and you're trying to calculate the amount of one substance, think about how do I get moles of another substance in that balanced equation. Okay, so if you know moles of another substance, you can basically convert it to moles of the substance that you're looking for, the amount of the substance that you're looking for, using the molar ratio from the balanced equation. Okay, okay, here's another problem. How many moles of oxygen are needed to completely burn 1.0 kilogram of hydrogen? So you're given this number, 1.0 kilograms of hydrogen, and you're looking for moles of oxygen. So that's our desired unit. So again, if you're looking for amount of any substance, think you basically are given amount of a different substance. So here I'm looking for oxygen and I'm given the amount of hydrogen. Okay, you can relate these two using the molar ratio. If you have moles of A, you can go to moles of B. Okay, but here I'm not given moles, so I need to convert this to moles. So remember, if you have mass, here mass is given to me. So if you have mass in grams, basically, so let's say if you have mass in grams for A, you can convert it to moles using the molar mass of that substance A. Okay, but here we have kilograms. So first we need to do an extra step. We need to convert our kilograms of the substance A. Here your A is basically hydrogen. Okay, you want to convert kilograms of your substance to grams of the substance. So that's our first step, kilograms to grams. The reason is once I have grams, I can go to moles using the molar mass. So we know there are 1,000 grams in 1 kilogram, and kilograms cancel out. And next we are going to change our grams to moles, grams on the bottom because we need to cancel out grams and go to moles. And these are related by the molar mass of H2. Molar mass of hydrogen is 2.02. So a mole of hydrogen is 2.02 grams. And once you have moles of hydrogen, you can go to moles of oxygen. You can go to moles of the different substance, oxygen here, using the molar ratio between those two. And the molar ratio between hydrogen and oxygen, as you can see here, it's 2 to 1. If 2 moles of hydrogen are used, 1 mole of hydrogen will be used as well. One mole of hydrogen will be used. So we put that ratio, cancel out moles of hydrogen, and that's how we get moles of oxygen. Here, the number is 247.5. And since we have two sig figs here, we have to round this off to 250 moles of hydrogen. Okay? So we can think of different variations of this problem. Okay? But the key is this, what you have learned here. Moles of one substance to moles of another substance using the molar ratio. Okay, instead of being directly given moles, you could be given grams. Or here's a nifty chart. This is your key, moles of A to moles of B using the stoichiometric factor or molar ratio. You could be given grams. Instead, you could be given volume. Okay, if volume is given, then you can change volume to mass, and then mass to moles using the molar mass, and then go from moles of A to moles of B. Okay, and you may be asked to report the quantity of B in grams. So you could do an extra step, converting moles of B to mass of B using the molar mass of B. Okay, here's the problem to illustrate this further. An SUV features a 60-liter gas tank. Assuming complete combustion and a molecular formula of C8H18 for gasoline, approximately how many grams of oxygen is consumed per tank of gasoline? Assume a density of 0.78 grams per milliliter for gasoline. So if you look at what unit you're looking for, it's grams of oxygen per tank. Look at this. How many grams of oxygen is consumed per tank? So let's underline that. That's the unit we are looking for. Grams of oxygen consumed or used per tank. And for what? For what are we looking at grams of oxygen? Basically, per tank, that means per tank is the tank basically contains 60-liter gas. So you're looking at how much oxygen is needed for 60-liter gas. Okay, so 60-liter gas is what you have per tank. So that's the information you're going to start with. Okay, so let's write that down. You're looking, if you have 60 liters of gas and you're asked to assume that the formula for gasoline is C8H18. Basically, gasoline is mostly made out of this compound, and the name of this compound is octane. Okay, for simplicity, here we are assuming that the entire gasoline is made out of just this. Okay, so instead of gas, I'm going to write 60 liters, 6 C8H18, which is octane. And if you know this, then based on this, how would you calculate grams of oxygen consumed or used per tank? This is your given, and this is your what you're looking for. Now, rest of this is all conversion factors, or you have to think about a way to get from here to here. How do we do this? Remember, anytime you're converting between two substances, they are connected by a balanced chemical equation. Okay, so this is a combustion reaction. So note that a combustion reaction is always a reaction with oxygen. So oxygen is going to be one of your reactants. Okay, so since you're burning this gas, so this is one of your reactants and oxygen is the other reactant. Okay, let's put those on the reactant side. The gas reacting with oxygen or burning in the presence of oxygen. And your products for combustion of hydrocarbons are always water and CO2. Hydrocarbon is basically a compound made out of hydrogen and carbon, okay? And this is a hydrocarbon because it's made out of only carbon and hydrogen. And when you burn hydrocarbons, you get always water and CO2. So those are your products, CO2 and water, okay? So let's put them on the right hand side. We have a reaction, but this is not balanced. So our second step will be balancing. Okay, first step, write the reaction. Second step, balance it. So how do we balance this now? We have 8 carbons here. So you put a coefficient of 8 here so that you have 8 carbons on the right hand side as well. You have 18 hydrogens on the left. So you put 9 there because 9 twos is 18. So you have 18 hydrogens on the right as well. You have 18 hydrogens on the left, 18 hydrogens on the right. Now count the oxygens. So from here you have 8 times 2, that's 16, and plus 9 times 1, so 16 plus 9. That's a total of 25 oxygens on the left, sorry, on the right. So how do you get 25 oxygens on the left? So if you put a coefficient of 25 over 2, then 25 over 2 times 2 is 25. Okay, so this is mathematically correct, but we cannot have fractional coefficients. So you double everything up. So the coefficient here is 1. When you double it, you get 2. So the coefficient here becomes 25. The coefficient here becomes 16. And there it becomes 18. Okay, now we have a balanced equation. If you want, you can check, you can count oxygens. You have 25 times 250. You will also have 50 oxygens on the right if you count them. Okay, so at this point, I want you to stop the video and figure out for yourself how to get from here to here. I'll get to the answer in a few minutes. All right, so let's discuss the answer. So we are connecting liters of octane to oxygen, okay? And octane and oxygen are related by the molar ratio, okay? So to convert octane to oxygen, to be able to use this molar ratio, you have to first translate this information to moles. If you have liters, we know that this is volume, and volume can be connected to grams, which is mass. Volume can be connected to mass using the density, and then mass can be connected to moles using molar mass. Okay, so let's go ahead and do that. Since volume in here is in milliliters, your first step would be changing liters to milliliters. So that's our first step. So we are gonna say 1 liter, and let me go ahead and write the substance out. So we have octane. So 1 liter octane means 1,000 milliliter octane, C8H18. Okay, all right. And now liters of octane cancels out. Next, we're going to go from milliliters of octane to its mass in grams, grams of octane. And the connecting factor is the density. There is 0.78 grams for every milliliter of octane. So 0.78 grams for a milliliter of octane. And now milliliters cancel out. Next step, you're going to go from grams of octane to moles. Always remember, to connect two substances, you need first the information, one of the information in moles. Then you can use the molar ratio. Okay, so that's what we are doing now, going from grams of octane to moles of octane, And grams and moles of a substance are connected by molar mass. So we need to get the molar mass from the periodic table. So if you have a periodic table, you can go ahead and calculate the molar mass of C8H18. It's basically 8 times carbon's weight plus 18 times hydrogen's weight. If you calculate that and put the units in grams per mole, that's your molar mass. I got 114.98. Please go ahead and calculate and check my answer. So I put the number there. So I have 1 mole of octane is 114.98 grams. Okay. Now, once I have moles of octane, I'm going to go from moles of octane to moles of oxygen using the molar ratio. For 2 moles of octane, you will use 25 moles of oxygen. So that's the molar ratio we are going to put. Okay, so 2 moles of octane uses 25 moles of oxygen. Okay, now our last step is to convert moles of oxygen to, so moles of oxygen to grams of oxygen, using the molar mass of oxygen. And the molar mass of one mole of oxygen will weigh 32 grams. So I'm going to put 32.00. We use molar masses at least up to 2 decimals. So 1 mole of oxygen is 32 grams of oxygen. So the units cancel out, grams and grams, moles of C8H18 cancel out, moles of oxygen cancels out, and then you will be left with just grams of oxygen per tank. So that's the final unit you're going to be left with, basically this unit, grams of oxygen per tank. Okay, and if you go ahead and calculate the number, you should get, I got 162,810.09, that many grams of oxygen. Okay, so let's rewrite that. We have to round off to 2 decimals. Sorry, 2 significant digits, because there are 2 significant digits in both these numbers. So that's going to be 16. You're going to round off there, but you need placeholders for these. Okay, so you have 16 and then 4 zeros after it. And that many grams of O2 is used per tank. You can say used or consumed per tank. Okay, there's your answer. Next, we are going to look at percentage yield. This is the last part of this video. Percent yield is experimental yield over theoretical yield, this fraction times 100. So what is theoretical yield? Theoretical yield is basically what you calculated using stoichiometric ratio. So you can call this calculated value of how much product you produced, okay? Uh, Experimental yield, on the other hand, is what you actually produced in the lab. So suppose somebody did an experiment. They would have calculated how much of a certain product they should have produced, but they would have got only a lesser amount than what is predicted. The amount actually produced is the experimental yield, and it's always less than the calculated value. The reason is you may have lost some product because your starting materials are not 100% pure. Your calculation may be assuming that they are 100% pure, but in reality, if the starting materials are not 100% pure, the amount of product that is generated is going to be less than what you predicted. Another reason why your actual yield is low could be because the experiment itself may not be 100% effective. Um, there could be some side reactions going on. So some of the um, reactant could have been used in a side reaction. So the actual amount produced may be amount of product produced may be less than expected. Another reason is human error. Sometimes you could lose the product in a filtration step, so you could end up with less than what you predicted. So since experimental is always less than theoretical, this ratio is less than the number 1. And so your value calculated when you multiply it by 100, the percent yield is always less than 100, okay? Now, why is this important? Why should we care about percent yields? Usually in industry, the concept of percent yield becomes very critical, especially when you have multiple steps. So let's say you have a pharmaceutical reaction, which is a 6-step process. Let's say the yield in each step is 90%. Okay, so what is the overall yield at the end of 6 steps? So 90% means 0.9. 90 over 100 is 0.9. So in the first step, you would have produced 0.9 of what you had. And in the second step, it will be 0.9 of what you got. So if you keep doing that, 0.9 multiplied 6 times is 0.53, which is 53%. Okay, so you lost almost half of your starting material. So percent yield becomes important to estimate the amount of product that you got at the end of the reaction, especially if you have multiple steps and each step is not very effective, then you could end up losing a lot of product by the time you get to the end. So here's a sample problem on percent yield. Um, here's a reaction, acetylene. This is acetylene undergoing combustion to produce carbon dioxide and water. So the problem says 25.02 grams of CO2 was produced. So this much was produced when 10 grams of acetylene undergoes combustion. So when 10 grams of acetylene undergoes combustion, they provided you a value for how much CO2 you got. So that's the actual yield. This is what that has been produced. So I can say this is my actual yield of CO2. Now they're asking you what is the percent yield. So to calculate the percent yield, you need theoretical yield as well. So you can predict the theoretical yield from a calculation starting with 10 grams of C2H2. You can predict if you have this much, how much CO2 should have been made. Okay. So here's the molar masses of C2H2. You can use that to convert your grams of acetylene to moles of acetylene. And once you have moles of acetylene, you can go from there to moles of CO2 using the 2 to 4 molar ratio. And once you get moles of CO2, you can convert that to grams using the molar mass of CO2. So here are the steps. Grams to moles, moles of one substance to moles of another substance using the molar ratio, 2 to 4. And then once you have moles of CO2, we calculated grams of CO2 using the molar mass. Now this number is how much CO2 you should have got if you used that much C2H2. Okay, so we're going to call that theoretical yield because it's predicted from a calculation. So now the actual yield, the percent yield is going to be actual over theoretical times 100, which when actual is this number, okay, theoretical is that number, which when calculated and rounded off to 3 sig figs is going to give you 74.5%. So this is the answer. Okay, so now that we know how to do stoichiometry, let's add one more step, how to predict the product if amount of 2 reactants is given to me. Okay, that's where we are treading into the waters of limiting reagent, which you explored using nuts and bolts experiment last week. So that's what we are going to discover in the next video, the limiting reagent concept.